Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 177, I chat with Anthony Grimani about the importance of room acoustics and acoustic treatments. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CacheFly.com.
This is Home Theater Geeks with Scott Wilkinson, recorded October 7th, 2013. Episode 177, Acoustics 101. Hey there, Scott Wilkinson here, the Home Theater Geek and Director of Content at avsforum.com. This week's guest geek is Anthony Grimani, a world-renowned acoustician and president of MSR Acoustics, makers of acoustic treatments. And obviously, we're going to be talking about acoustics today. Hey, Anthony, welcome back to the show.
Hi, Scott. How are you?
I'm great. Thank you. Anthony
Fantastic.
was one of...
I'm going to interrupt you. You forgot to say that I am also an extreme geek.
That's true. Pardon me for missing that. Yes, Anthony is definitely an extreme geek. He actually has a D65 light on him for the video, those of you who are watching the video. And so, yes, he's definitely on the geek side of things. Well met and well matched to a show called Home Theater Geeks. Yeah, and in fact, you were one of my very first guests, like in 2010. So it's well overdue for you to have a return appearance, and I'm glad to have you back on the show.
Glad to be back. My pleasure.
Now, those of you who are watching live at live.twit.tv or logged into the chat room at irc.twit.tv can post questions for Anthony, and I will pass along as many as I can. Okay, so obviously we're going to be talking about acoustics today, and in particular room acoustics as they apply to the home theater. So why don't you run us through some of the basic concepts that people really should be aware of when considering the room in which they are going to put their home theater. I've often said, to start with, you need to consider the room as a component, much like your AV receiver and your speakers. It's another component that contributes to the overall experience.
Yeah, Scott, it's definitely a component. The room is really the final interface between your loudspeakers and your ears, and it will morph the sound. It will distort it. It will add some parts. It'll subtract some other parts. If it's not controlled correctly, it'll actually fight your speakers, and no matter how good the speakers are you selected, you may hear substandard sound. I have a little PowerPoint presentation prepared, and maybe I'll ask John to hit the first button, see if that can pull up here. Very nice. So I like to think of this acoustic interface. So we've all been talking about electronics products and loudspeakers and the interfaces with them. If you can hit click for the next one. So right now, John, go ahead and hit and click. There you go. Right now, this world, which is the world of the boxes and the wires that connect source devices to surround processors, maybe equalizers, certainly power amplifiers. That world has been studied. It's very well under control. The interface is available from many, many different cable manufacturers today, are fantastic. Then we're going to take this pristine sound coming out, or pristine signal, I should say, coming out of the power amps. We're going to feed it to loudspeakers in a room where the sound could bounce around randomly. So if you hit click, you'll see what happens. Signal goes to speaker. You get one direct sound from the speaker to the listener, and then you have a bunch of off-axis sounds, those that don't hit your head but go over to the walls, the ceiling, and the floor that bounce around. If you're lucky, and extremely lucky, I'm actually talking very lucky. I'm talking that you could win the lottery lucky. The interface between the loudspeaker, the room boundaries, and the listener is actually constructive and is so for all 5 or 7 loudspeakers you have in the room. Most of us are not that lucky. And in most cases, we're not winning lottery tickets, and we're also ending up with substandard sound. So in a way, you got to think of some of the sound reflections that happen off the walls of the room as potential distortions. So let's go to the next slide real quick. And I just wanted to illustrate that if you imagine you have a room with hard surfaces, sound of a saxophone's coming out of the center speaker, part of that sound's going to go to your seating position. Some of it's going to bounce off the left wall. And that bounce means the same sound gets repeated twice, once from the speaker directly, and then a second time after it's bounced off that wall and come back to you.
And that reflected sound is going to reach you at a slightly later time.
Typically 5, 6, 7, 8 milliseconds, depending on the size of the room.
Right.
So now your ear and your brain hears the same saxophone twice. Once coming from the speaker, once coming from the left wall, then maybe the right wall, the floor, the ceiling. And now it has to do all this work to untangle what's the real saxophone versus the one that's coming from all these other places. And the ear-brain mechanism of a human being actually does that pretty well, as long as it's within certain limited range of reflections and as long as it's not too many loudspeakers. So you do want to take control over this to a certain extent. And the control could be the use of sound absorbers. So let's click to the next slide. Sound absorber is some kind of panel or material you put on the wall of the room that converts the moving sound particles, the moving air particles that are interpreted by the ear as sound, and turns it actually into heat through friction. So it's typically a fibrous material, either fiberglass or rock wool are the two most common materials, and they basically absorb out the sound. Just don't let it return to the seating position. You don't want to put too many of these. You want to have just the right amount, and I'm going to talk about that in a second. Another way to control that bounce is to use what's called scattering. If you can advance to the next slide. Here's an example of scattering. Sound from the saxophone goes to your listening position. The off-axis sound, the one that goes through the wall, stays in the room, but it's been scattered into little pieces, just exploded into smaller parts that are less offensive. When they get back to your head later, because they're not as loud and they come from many different places, the brain has an easier time at processing that out. So how much of the sound reflection actually exists in a room can be interesting. Let's go to the next slide. So here's a room seen from above where you have that's you, the listener in the middle, receding hairline in the middle of
yeah, that's me, all right.
Yeah, right there, see?
And it looks like a seven channel system. You haven't put the subwoofer into that diagram, it looks like.
Correct. I'm just talking about the main speakers here. We'll talk about the subwoofers that are really, really important. I'll get to that towards the end. But here's you in the middle of 7 loudspeakers, all squirting sound directly at you and all reflecting sound off all the boundaries. And at some point, your brain goes into saturation mode going, you know what? I can't deal. I hear a whole bunch of direct sounds coming to me. I hear a whole bunch of reflected sounds. And I'm just going into basically your brain goes in shutdown. It goes on strike and goes, I don't know anymore. I'll just make it sound like it's coming from everywhere. And your directional abilities just get reduced and your intelligibility gets reduced. So let's look at that slide again. Let's hit click and you'll see, just get back to the most important channel in here, which is the center channel. When the sound comes from it, there's a direct sound from the speaker to you. If you hit click, you'll see that. That's the green arrow in there.
Well, we don't see it quite yet. Might be having a little trouble there. There it is. Here it comes.
That's the intended direct sound from the speaker to your listening position. That sound has been carefully crafted by the sound designer in cahoots with the director and all the people working on the sound. There's a certain character to that. Let's hit click again, and you'll see a sound vector that just passed you. That just passes you. Doesn't quite make it to your ear, but instead it just passes right past you here on your, in the case of this diagram, your right side. And then it bounces off the back wall, bounces back on the front wall, hits the right wall, hits the back wall, and finally gets back to you after it's bounced around. And after all of that, it's a full 20, 30 milliseconds before you hear it. Let's look at another sound, like another 10 degrees off axis. It bounces around a different set of boundaries and gets back to you later. Let's go another 10 degrees past that with another button click. Here's another bounce. It hits off the wall here, the wall's there. Basically, all these off-axis sounds, as they're known from speakers, the sounds that don't go directly from the speaker to you, but instead hit the walls, they all bounce around and get back. Eventually, they pass your head at different times. So the direct sound's the first one.
All of these reflections that we're seeing on the screen, I hope that I hope a lot of you are watching this because it's really very cool. But that's just from one speaker.
That's one speaker.
That's just from the center speaker.
It's only the center speaker and only the right side of the room so far. So all of that stuff that doesn't hit your head, but instead goes through the room and bounces around, eventually passes your seating position and gives you the same sound after the original one, another one, another one, another one, another one. They do decay in level. After a certain time, the level goes down. But that's a lot of red lines hitting your head from the right side. Now, what about the left side? Well, good speakers don't send sound to the left. No, that's not how it works. Let's hit another click, and let's be leftist about this or centrist. And I kid you not, this is the web of sound energy that's bouncing all over your room, sending confusing messages to your brain as to what the real sound is. And again,
that's only from the center speaker.
That's only the center speaker. So if you're watching My Dinner with Andre, where everybody's speaking out of the center speaker for 2 hours, that's all you get. If you're watching any other movie, this same pattern gets reflected out of the right speaker, the left speaker, the surrounds, the backs, all over. I don't know what you call that, but I call that saturation. I can't deal.
Right.
I put in there that chaos reigns, and sometimes it is chaos. You get to a point where you're just like, man, I can't understand what they're saying. I need to pause for another glass of scotch. Maybe I'll quit watching this and I'll, read a book instead. Maybe I'll go to the latest podcast from the Home Theater Geeks because that's a lot more restful. It's a mess.
Thank you very much. Thank you.
Yeah, you're welcome. So let's go back to the slides. Now, you may notice that through all of this mess, you do find that the sound comes from the speaker. So let's go to the next slide. And in reality, what really the perception of the sound here, I put on the top, I said I put sound field perception and then direct sound dominates. There is a mechanism in the ear brain of a human being that's always tracking where's the first arriving sound, whether it's here or there or wherever, and is looking at when the next, the similar patterns of sound are, but that are arriving later in time, and is deciding, okay, that was the first one. This is a later one. I'll ignore the later ones. I'll just pay attention to the first one and everything will be fine. And that's really how you go about your listening every day. You're confronted with sound reflections all the time, more or less of them depending on what goes on. And you can generally tell the sound's coming from over here until you get really old. Because as you get old, this mechanism in your brain just starts to break down. Your auditory system breaks down. And you'll notice that as you get older, it gets to be harder and harder to be in reverberant spaces. And as we get older and our parents and grandparents get older, you notice how they have a harder and harder time at the dinner table to even follow a conversation. So the human brain can kind of cut through all this and untangle it and go, okay, there's a center speaker as long as the chaos is reasonably controlled. And that holds true until you have 7 of these things squirting at you and you just overload. So that's the reality of what most people are listening to, whether it's 2-channel or 5-channel or 7-channel audio with or without a subwoofer.
Now, in this case, the room is pretty reflective.
I'm
right?
taking
the walls and ceiling, yeah.
I'm taking a case of a 7.1 channel system in a room that's all got reflective surfaces. It's all hard. There may be windows. There's walls. There's a hard floor. There's no special materials that damp the sound. Nothing that's out there to soak it up.
Right. Now, before we go on, Da Vinci Wonder has a related question in the chat room. Doesn't the sound intensity drop off something like the square of the distance, effectively making the later sounds insignificant?
That is correct. Now, the square of the distance rule is in an anechoic environment. So that's if you actually look at the distance over time, as the sound spherically spreads into the room, that is what the intensity loss is. It's a little bit through absorption in air. The air molecules actually have to all slam into each other. And they lose some energy all the time, but the bigger part of the energy loss is just that it's dissipating spherically.
Right, and that's, as you say, that's in an anechoic environment, which means no reflections. Typically, you're talking about outdoors.
Outdoors, exactly, or in an anechoic chamber if you have the great chance to live in one of those. And I don't wish that upon anybody.
No.
I'm surrounded by fuzz. I love it. So the in a room, the sound intensity loss is actually more 3 dB per doubling of distance is sort of the prevailing thought, which instead of being doubling, it's actually instead of going 0.5, it's going 0.7 per doubling of distance. Whatever. The reflections,
so in other words, it's decreasing less drastically than it would in an outdoor environment.
Exactly. Maybe you could, say 30% per doubling of distance. So
right.
I did mention at some point that the reflected sound, if this was a representation of an impulsive sound and time was going in that direction, the next sound, after the first reflection, it would be a little quieter. And then the next one would be a little quieter and a little quieter and a little quieter. And actually, if you looked at these reflections on a decay, on an actual way to measure what's called the impulse response, you will see that the reflected sounds decay down. Now, they decay down, but the total energy of those reflected sounds is actually 2 or 3 times louder in total power than the direct sound in a typical room without special treatment.
So they are going to definitely be easily perceptible and maybe even overwhelm the direct sound.
Definitely and definitely.
Deafeningly. All right.
So let's go to the next slide, and I'll suggest what some people try to do, which is to go, well, if reflections are bad, I'll get rid of them all. Just kill them all, and that's called an anechoic space. The way you would do this, for example, is to put heavy draperies all the way around the room, or better yet, 6 inches of dense fiberglass insulation that you cover with fabric all the way around. And if you do that, the first thing that's going to happen is you will have exclamation question mark coming out of your brain. So let's click forward. First thing is humans like some amount of reflections. There's a normal amount that you expect out of a room. Next, click forward. If you eliminate all the reflections, you're actually going to confuse your brain way beyond the chaos I mentioned before. It's actually better for the human being to be in a space that's reflective than one that's completely dead, because you're used to hearing reflections and you're used to working through canceling them out. You remove that sensory effect and your brain does go into like, whoa, what's going on around here? And those of you listeners who happen to have been into an anechoic chamber one day because you were visiting a speaker manufacturing company or something, that have stood in there for a little while, notice that you start to lose your sense of balance. You start to hear weird sounds in your ears. And it's not a pleasant place to be in. So don't do this. It really isn't.
Yeah. Well, I mean, I would recommend doing it if you can, just to experience it. But you don't want to do that in your room.
Sure. Don't do this in your listening room. Right. So let's go to the next slide or next click. And so you need to preserve some amount of reflections. The question is, how many do you want? You want just the right amount so that they support the loudspeaker rather than work against the loudspeaker. That's the main trick. So here's where the work I've done over the last 20, 25 years comes in. I had a chaotic accident of excess reflections in a demonstration at a trade show about 25 years ago, where I had great electronics, great loudspeakers in a room that was all reflective, and the surround sound effects were dead. It was all giant mono coming out of everywhere, and it took me a while to figure out it was the room reflections, and I fixed those in this case by just putting blankets and bedspreads all the way around the room. It looked horrible, but it sounded great. There's a better way, and the way is to think in terms of simple recipes. So let's go to the next slide. 25 years of work has led me to believe that this recipe works. If you click forward, if you cover the walls with about 20% of absorptive surface, and those could be draperies, better yet, real absorptive materials made by manufacturers that focus on making those well, and you distribute those evenly in the room, where you don't all put them in one place, but you actually stripe them all the way around the room, you will now lower the reflected energy enough that your ear-brain system can actually have an easier time at figuring out what's real from what's all the reflections around. And that particularly applies as you start to multiply the number of speakers around the room.
Now, when you say 20% absorption surface, you mean 20% of the surface area of the inside of the room?
Yeah, exactly.
Are you talking about the walls, also the ceiling and the floor, or?
So walls and ceiling are important. The floor would be nice to do. Usually that's done by putting an area rug. The ceiling, you can sometimes back off from that and maybe only do 10%. But by and large, around the room, if you can do 15 to 20% and no more, you will end up with a much better clarity, much better soundstage, much better ability to hear the difference between left and right, front and back, and just a more restful experience, something that's less fatiguing after 2 hours of a big action movie.
Sure. Okay, cool.
So let's go back to the slide and click forward. What we've also found is that it's really nice to scatter some of the reflections. So at this point, if you only cover 20% of the surfaces with sound absorption, that means you have 80% of the wall surface still banging sound reflections around you. And if you can cover about 25%, these are rules of thumb. If you can actually do 20 to 25% of diffusive surfaces, those are surfaces that don't absorb the sound but scatter them back out in various directions, you will end up with the next phase of sound quality, which is the sense of spaciousness and integration between the speakers. Instead of hearing individual speakers placed around you, you'll get the sense of a sound field that's really nice and even all the way around you, and actually tricks your brain into believing you're in a bigger room than you really are in.
And again, this 20% and 25%, you're talking about surface area. There was somebody in the chat room who asked about this. 20% of Eric Duckman, 20% of the surface, not, quote, 20% material. I guess that it would absorb or diffuse 20% of the sound. That's not what you're talking about.
No. 20% of the surface. So if you had a room that was 20 feet long, 20 feet long by 10 foot tall, the left wall is 200 square feet. You want to do between 15 and 20% of that in absorption, and between 20 and 25% of that in diffusion. Some material that can scatter the sound around. I think I've got some nice slides that show what those kind of materials can be, but the main idea is to break up the sound into little pieces that are floating around the room, giving you a sense of being enveloped by sound and helping in the sense of realism and integration in the sound field.
Mm-hmm. Go ahead.
So I'm sorry, go ahead.
Oh, I was going to say, Web7478 in the chat room has said, what about a homemade baffle wall? Will it also help controlling sound waves from speakers to listeners?
So I think I know what you mean by a baffle wall, but tell me, is that a wall in the front that the speakers are placed in, or is that something else?
Well, it's a good question. Web7478, let us know what you mean by a baffle wall, and hopefully Anthony will be able to answer it.
I'm baffled by your question. Let's go to the next slide.
So in the meantime, let's go to the next slide.
See how much fun I have with this stuff. It's an enjoyable profession. I'm lucky.
Indeed.
So you already mentioned this, Scott, but make sure you have some treatments on the ceiling of both absorption and diffusion. I tend to like absorption in the area between the listening zone and the speakers, and some diffusion behind you. And I'll show you some diagrams of that.
Before we go on, let me just ask you this: most speakers act as more or less point sources, and the sound radiates out of them originally spherically, as you mentioned before. But I wanted to point out, and that also then means that the things will get reflected off the ceiling. Mm-hmm. Pardon me. The Wisdom Audio, for example, at CEDIA, which we were both just at, They specialize in speakers that are called line arrays, which are tall, vertical columns of speaker drivers. And they claim that those are much more controlled in their vertical dispersion. So if you had line arrays in your room, would you have to not worry about the reflections off the ceiling and floor quite as much?
Yeah, that's a great question, Scott. Yeah, line arrays, a proper full line array, which is a source of drivers. There's different technologies used in the drivers, but basically by lining them all up vertically, it creates a focus of sound towards the listening area. Essentially, it removes actually all sounds above the top of the column and all sounds below the column. There's a very simple wave theory physics that goes behind that, and I don't want to get into that or we'll get really bored. But the bottom line is that those speakers tend to radiate like a cylinder without spraying vertically top or bottom. And with those speakers, you don't have to worry as much about the ceiling and floor.
Right. Okay. That's what I just wanted to verify that. Luis in the chat room is asking, are those percentages evenly distributed or all in front of the listener?
So the first, the simple answer is evenly distributed. And again, I'll show you a diagram that shows some of those things. If you have either a lot of time to mess around with the acoustics, or you can hire an acoustical consultant, such as, my company has a consulting division. There's also a whole bunch of great other consultants out there. You can refine that by figuring out where's the best place to put this or that. But if you start off by just placing these things evenly around you, interleaving the absorption with a diffusion, absorption, diffusion, absorption, diffusion, that will get you, I would say, between 85 and 90% of really, really good sound. And by that, I also want to indicate that this old theory from the 70s of putting all the absorption in front of you and all the diffusion behind you has been shown repeatedly in research and listening tests not to be the best way to go about it.
Okay, so alternate them. Absorber, diffuser, absorber, diffuser. Now, I've heard you say that diffusers, if you don't actually buy diffuser panels made for the purpose, you could use something like bookshelves.
Yeah, and Scott, any shape that's a broken shape, that's not hard, reflective, will naturally scatter the sound. So a bookshelf, especially with the books at different depths, will be a diffuser. You don't really know what kind of diffuser it's going to be. You're not really sure if it's going to refocus the sound this way or that way or around, but it's better than just having a hard, flat surface without any control.
Got it. Okay, you were about to go to the next slide, and I interrupted you. My apologies.
No worries. So let's click forward to the next. It's still the same slide, but next point. And that point is that, hey, don't forget the bass absorption. Everything I'm talking about so far in small room acoustics, which is rooms up to about 50 or 60 feet, is really mid and high frequency effects. We do need to worry about controlling the bass character, and I've reserved that sort of towards the end of the presentation here. Bass tends to pile into a room differently than mids and highs, and there's different topologies for dealing with those. So let's go to the next.
Weeb in the chat room is asking about that, bass traps in particular, and whether or not they're necessary in the corners. And I know you're getting to that, but I just wanted to let Weeb know that we'll get there.
Weeb, good bass traps are necessary in the corners. Like they say in Latin, caveat emptor, which means watch out, you may be sold the wrong thing. There's a lot of companies making and selling things they call bass traps that really are only mid-bass absorbers. They don't really control the low frequencies, and that's usually where you have to worry about stuff, is in the region between 30 hertz and about 100 hertz. I'll get back to that.
Okay.
So I'm getting back to that diagram we had before with all the chaotic lines everywhere. And I'm putting in this diagram a suggested layout for various panels around the room for absorption and diffusion. And I'm going to show you what would happen to the sound reflections if you do that. So we have a room over here that's showing us our direct sound from the speaker to the listener. And then off axis, by some absorption, some scattering, you're either damping out the sound, so trapping it out, or scattering it back into the room spherically or hemispherically, back towards the listening area. So this is the right side of the room, and that's the left side of the room. This is our, after, I'd say 20, 25 years of trial and error, reading all the scientific literature out there, all the people who are doing core research on listening and the perception of listening, which is, by the way, called psychoacoustics. There's actually people out there who have a career in psychoacoustics, and they are called psychoacousticians.
As a matter of fact, I co-taught a class in psychoacoustics when I was in college, and I find it to be a fascinating subject.
I always thought you were a little psycho. No, I'm pretty sure about
Now you know.
Now I know where that came from.
Dr. T in the chat room is asking, looking at the placement examples on your website, there are no panels installed in the front of the room at all. And yet on that diagram we just saw, you did have some panels on the front of the room.
Absolutely. I'm trying to build something sort of conceptually pretty simple. And if we had 6 hours, I'd show you the real advanced thing. But so in this room, we're placing absorbers and diffusers on the side walls and on the back walls of the room to create a controlled sound field. We're damping out. Remember, we're damping out about 20% of this reflected sound. No, only 20%. We're scattering about 25%. And on the front wall of the room, we're putting bass absorbers. Loudspeakers, typical loudspeakers today, don't spread a lot of sound to the back of them. They only spread bass. And that's a good place to put bass traps and bass absorbers. So when you look at this diagram, these black blobs at the front represent low-frequency absorbers. I see a lot of people put foam or fiberglass panels on the front wall, and really what that's doing is absorbing the sound after it's bounced off the back wall and come back, and it's typically over-absorbing a room, so it's not a good place to put them. So here's what I'm suggesting as a good layout for treatments in a room. Other people have different opinions, but I find this creates a smooth and orderly sound field, which if we click forward, you'll see a conceptual character of that. So here's the direct sound, and click forward. This is the net room return. Oh, let's go back one more. This is the net room return of energy. Oh, back one more.
Back one more. There you go. Okay, now forward.
Seems to want to go on its own. It's fine. So there's a crescent of sound that provides a smooth immersion and a clear direct sound that gives you the clarity and intelligibility and localization you want. And then you have this immersion of energy from the rest of the room that makes you feel like you're there. And that applies to all of the speakers all the way around you. It works on all axes. So let's go forward one more slide and show you a pretty rendering of that same suggested layout, which shows a couch in the middle, 3 speakers in the front, 2 speakers on the side. I'm not showing the back speakers over here, otherwise it gets really chaotic.
Right.
But you can see in here in green all the absorbers on the walls, in the ceiling, the back wall, and you see the diffusers are the white materials that scatter the sound, all interleaved with the absorbers. Towards the front of the room, we actually are putting on the side walls towards the front. I suggest doing what's called a 2D diffuser, which is typically either a curved shape or a slotted shape if you use a QRD type diffuser that scatters the sound only in the horizontal plane, so that all of the sounds from the room are actually all traveling in this direction. That gives you a great sense of spaciousness. Towards the back of the room, I suggest putting 3D diffusers, which is a shape that's going to scatter the sound hemispherically. So the sound that hits the 3D diffuser tends to go up, forward, back, down as a
right,
hemisphere.
Left.
And that gives you a great sense of immersion for the surround energy you want in a home theater environment.
Got it.
I got to reposition my geeky Etymotic headsets. See, I don't have those big ear cans you have. I have
no, it's true. You have those beautiful
things.
little, yeah, but one's red and one's blue, so you know which one's in the right ear. I love it.
Exactly. Otherwise, I'd get lost.
I did have one question in the slide before that last one we just looked at. If you can pull that back up, John, there it is. What are the little checkerboard things behind the listener?
So those are 3D diffusers on the ceiling of the room.
On the ceiling. I gotcha. Okay.
Ceiling, yeah. And if you go forward, you'll actually see those again in the perspective view.
I see. They're right over the...
Now,
yeah.
Well, actually, the perspective is a little confusing. They look like they're right over the listener, but actually they're... I recommend putting them behind the listening position, maybe 2 or 3 feet behind the listening position. And if you could turn that 3D rendering sideways and look at it on an elevation view, you'd see that they're behind.
They're behind the thing. Okay.
Yeah.
Luis in the chat room is asking, it might be from the diagram, but my impression is that there's about 50% of walls untreated, absent from the diagrams. These diagrams that we've been looking at seem like there's more than, well, you know what? Now that I'm thinking about it, maybe not. When you take a look at the absorbers, those are the green ones, right?
Correct.
In this one. So, okay, there's maybe 20% of the wall area taken up by those, and then about 25% taken up by absorbers, which means that roughly half the surface of the room, of the walls anyway, and the ceiling, are not treated.
Correct.
And that is, in fact, what it looks like there.
And that's what we found. You know, we've tried putting more absorption, less absorption, more diffusion, less diffusion. You put too much diffusion and you end up with confusion. Is actually a very good... I didn't invent that. There's a great scientific paper published in the Audio Engineering Society journal on a research of, you know, how much diffusion do you put in a room? And you put enough of it and your brain goes, whoa, there's too much scattering here. I can't tell where things are going. Too much absorption, the room sounds dead. It loses its life. The music is not supported correctly by the room. There's a very careful balance. And I guess that's I would say my main message is today is you got to damp the sound reflection some amount. Damping them, by the way, it's not dampening, but it's damping. Dampening is the action of putting water on the walls,
Right.
which is what you have to do to get rid of that really ugly wallpaper that's still in there.
Right.
You want to damp out some reflections. You want to scatter some reflections, and don't treat the room any more than 50%, or else it's going to start to sound unnatural.
Got it.
Let's go to the next slide.
Mm-hmm.
And you know, this is sort of my conclusion. My acoustics really is, let's click forward, is the study of the interface between the speakers in the room around the speakers, and the listener. It's that interface needs to be taken into account when you're building your home cinema. And if you click forward, I would say it's a key product. After you get to all the great loudspeakers we can get today, even at very reasonable prices, you can buy amazing loudspeakers. And they're great surround receivers and surround decoders that, again, you know, I'm going back 25 years, what you had to spend to get something really good. It's a fraction of that today. So now that it's really relatively cost effective to buy great AV gear for the sound, and you go, okay, well, what do I have to do next? It's really about controlling the acoustics of the space.
Right. Now, Tinker Toy Tech in the chat room is asking, how do you get this past the wife acceptance factor?
Nice dinners.
Yeah, right.
Really nice dinners.
Jewelry, flowers work well.
Jewelry, preferably if you can cook the dinner. That goes a lot further. So you know, practice your cooking skills. Watch cooking shows and make a nice dinner, and then good luck. So I'll be the first to admit that this is really ugly on the walls of a room, and really not desirable for a living room environment. So the way I've gotten around that is actually you can hide all these panels behind stretched fabric that's printed. We have a line called Living Sound. If you look or poke around our website, you'll see that, where we take all these ugly devices and cover them with a printed fabric. You can either use pre-licensed artwork, or you can send your own artwork to be printed. And then you can maybe not apply the full 20 and 25%, but at least even covering 8 to 10% of the wall surfaces can go a long ways towards better sound. So let me actually take 2 seconds to show you some of these other things. So let's click forward. So over the years of doing all of this, we've realized that a lot of people are looking for easy solutions, and we've actually put in place a line of products that we call Dimension 4 to control the 4th dimension of sound. And if we click forward, you'll see these 4 systems. They're called Melody for the most basic one, Concerto for the next level one up, and then we have Sonata and Symphony, and they're arranged in actually 2 lines. The ones on your right are what I call architecturally arranged, which is the ones that have a better divorce or a lower divorce factor. The ones on the left are performance oriented. They're ugly. Okay, they typically, in most of the rooms we end up working in, get hidden behind stretched fabric. So that's a way to do it, is actually do a stretched fabric wall. And if we had more time, I could show you sample pictures of rooms we've done. But if you poke around our website and you look at those, you'll see examples of use, and you'll see that sometimes you can do this without it looking too ugly. Let me cover 2 or 3 quick things here before our time is up. There's our website. Wow, there it is. There's some examples of our living sound panels. We've got a new series of artful panels. There we go. Thank you, John. You're doing a fantastic job. You're hired.
I'm so happy he's on my show. Yeah, so go ahead. Tell us what you're going to tell us.
Yeah, let's click forward to the presentation. I keep saying I'm going to talk about bass a little bit later. Let's talk about bass. We have this is at the same time an advertorial, but more of an educational piece. There's this product we make called a spring trap. If we can click forward, it's our super high efficiency bass trap. It's this triangular box that sits in the corner of a room. It's a multimedia project made out of wood, springs, mineral wool, rubber gaskets, all kinds of different things. But the main important part is it works superbly between 30 hertz, closest to the lower end of where there will be standing waves in a room, up to 100 hertz, which is where standing waves tend to finish in most rooms. And this is an example of a room with spring traps in it. let's see, can you go forward one slide? Yeah. This is a cutaway view that shows how it's built. It's actually a panel mounted on precision springs that takes all the base energy that pressurizes it like a sail and compresses it into 3 different resonating Helmholtz absorbers, they're called, inside. And it, by this acoustic amplification of effect inside the apex of the triangle, we get really, really strong efficiency in the bass absorption way down, way down to 30 hertz. I guess in your direction it'd be this direction. So the next curve is a really geeky chart that shows...
Hey, we love geeky charts around here.
This is geeky. This shows the absorption capability of the spring trap as averaged over 2 seconds of effect in a room. So 2 seconds, what the heck is that? If you play a sound at the resonance frequency of a room, inherently a room is a resonating cavity, okay? It's going to ring at certain frequencies depending on the side of the room. You can hear the resonance changing here. Woo.
Right. And that depends upon the dimensions of the room and how those dimensions relate to the wavelength of a particular frequency.
Correct. A bigger room is going to resonate at lower frequencies, and a bigger room is going to resonate at higher frequencies. But at some point, it's going to resonate. At that resonance frequency, if the walls are stiff enough, because they're made out of solid material, not paper, but sheetrock, the sound could actually resonate around the room for a second or 2 before it dies out.
Right.
So let's say you have a kick drum in music. That kick drum, if it's at the wrong frequency, the one that resonates in the room, instead of being tight and punchy, it's going to go woo. It's going to actually sit in there for a second as it builds up and dies out.
So it's going to, in other words, it's the sound is going to spread out over time.
It spreads out over time. So the dynamics are lost. Instead of having a nice, punchy, rich sound, you end up with this mush of low frequency energy that rolls around the room. It may be exciting because it's loud, but it's wrong. Same thing for any, I use the example of a kick drum, but in an action scene in a movie, if you have a kablamo that's at the resonance of the room, just by bad chance, the sound designer created that kablamo somewhere around a frequency that corresponds to your resonance, it'll also sound mushy. Now there's some bad news here. Kick drums, usually, the main resonance of a kick drum is somewhere between 50 and 60 hertz. That's just where they are. Boom, 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 boom.
Right.
The majority of the energy put in a film soundtrack in the big explosive scenes is around 55 to 60 hertz. Those numbers come from just measuring and analyzing the frequency content of lots of movies and lots of music. Here's the bad news. Most rooms that are between 20 and 25 feet are going to resonate at guess what frequency?
50 or 60, 50 or 55
50
hertz.
to 60 hertz.
Yeah.
So you have the worst condition. You actually have us all sitting listening to home theaters in rooms that resonate at the frequency where most of the bass impact is.
Right.
So those of you listeners who may have noticed, hey, here's this great subwoofer I heard in the store. It was amazing. I brought it home, and it doesn't sound so good. It's slow, or I don't hear it, or I hear it too much. It doesn't integrate. That's all your room at work. It's not the subwoofer. It's your room messing it up.
Dang.
It's not easy.
So what we need are bass traps, such as your, it's called a spring trap.
Correct.
And I was going to mention earlier that correct me if I'm wrong, but it has a solid panel that is backed by springs. And when the bass energy reaches that, it gets transmitted inside this thing and damped, essentially, reduced.
It's damped, yeah. The panel is actually sealed around its entire edge with a foam seal, just like a subwoofer, like a woofer.
Just like the surround of a speaker.
Exactly, like a woofer, same material, butyl rubber, and it basically transmits centered at 60 hertz. Actually, if you go forward one slide, the peak of efficiency is right around 60 or 70 hertz, which is where rooms tend to resonate. At that resonance frequency, it transmits the molecular movement of the sound pressure into the cavities inside. And when those molecules go through the various resonating ports, as they have to actually squeeze through the little cavities, they actually create heat. As they go, they squeeze through there, the energy is converted into heat and dissipated out of the cabinet and just in heat.
Right.
If
Ingenious.
you play,
I mean, it really is.
Thank you. If you played 800 decibels for a long time, the cabinet may warm up by half a degree. Don't expect you can start cooking your eggs on a spring trap. That will not work.
Right. The amount of heat that is being generated is minuscule.
Is minuscule. An acoustician in England.
But it does transform the acoustic energy into heat energy.
Into heat. And therefore dissipates it out of the room through heat.
Right.
Anecdotally, a British acoustician published a paper a few years ago where he was trying to analyze basically the power of sound and convert the conversions into heat. How do you think of it in terms of watts of acoustic energy, and how that we all think we know what heat is. We don't necessarily know what kilowatts are. And the paper is like 10 pages of very complicated calculations with double differentials, big symbols that mean nothing to nobody except if you studied Greek. And in the end, he said, let's go ahead and run a calculation. And he took an example of a Beatles concert at Wembley Arena in the 60s, because he's British, right? So Beatles are it.
Of course.
And if you take all of that energy from the entire concert and could funnel it all, the 2 hours of the concert, could funnel it into a cup of tea, because he's British, a cup of tea.
Yes, of course.
You can funnel it all into a cup of tea. At the end of 2 hours, you would actually manage to heat up the water to boiling.
Really?
Yeah.
Wow.
That would be 2 hours of all the teen girls screaming, the band try to play over the teen girls for 2 hours, all focused onto one little cup of tea. Now, remember, in England, they use smaller cups than us. So
true.
that gives you an idea of the thermal conversion. It's not very much.
Right.
So let's go to the next slide. Next one after this, and then one more. So I get asked, well, what's the minimum thing I should do? Let's say I'm an audiophile or an audio-video file, and I can't put all this stuff in the wall. I just want to know what's the first Band-Aid? What's like the most important thing? And this is, I have the slide as like the first aid kit. If you really want to start with something important, I would say you need to have some kind of bass trap to control that rolling bass that's out of control. And then you need to have a few panels that provide some scattering and some absorption. And over the years, we've designed a product that we call the Trifuser SA, stands for small absorptive, that is actually this form of triangular shapes, really actually kind of attractive. I've had some partners of our clients that happen to live in the same house together and sometimes get upset about what goes on the walls. Sometimes when these things go on the walls, they go, wow, I like the new modern artwork you've put up in here, honey. That's cool. So we have success.
That's it. That's the ticket.
That's the ticket. So putting 6 of these things, they're 2 feet by 2 feet, putting them strategically in the room to get some absorption, some scattering, and putting some bass traps is the first place where you stop the bleeding, and the first place where if you do this, you'll notice, wow, this is already so much better. And then later with more dinners that you cook and serve yourself on a really nice white linens with candles, with nice music playing, you maybe can start adding some more panels later.
Right. Okay. Dr. T in the chat room is asking, where would you place those spring traps? Behind the sub?
That's a great question. There's the rough theory and the real theory. The rough theory says that any one of the 8 corners of a room are going to be equally pressured by what's called standing wave pressure. In reality, not so. Some are more energetic than others depending on the flexure of the walls. You know, the walls do tend to move a little bit, and they may change things. So given all choices, what I would suggest doing is actually playing bass in the room, either a scene with good bass or the test noise that's in your surround processor when it gets to the subwoofer and it's just going rumble, 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 and just go listen to the 4 corners at the floor level. And if you may find that 1 or 2 of those are louder, and those are good places to put the spring traps. Murphy's Law will say, of course, that one needs to go right by the door at the back where you can't put it, and the other one needs to go right by where your significant other partner has a beautiful plant, so you can't put it there. If Murphy is not busy or is busy doing something else that day, then it'll be in the front corners of the room, hidden behind the speakers where you would want to naturally put them aesthetically.
Got it. A couple people in the chat room have asked about, we've been talking about these nice rectangular rooms with boundaries all around, and it's a box, right? What about the rooms where it's open to the kitchen, or it's an odd shape?
Yeah. I got to start somewhere. So if I put up a picture that showed an L-shaped room with a triangular hexagonal thing, people will go, what? I don't get it.
Yeah, right.
So
you have to start somewhere, and rectangular rooms are the best place to start. They're the simplest case.
it's a good place to start. I do have to say this about rectangular rooms. There's a legend out there in the world of small room acoustics or even big room acoustics that says that the rooms need to be canted in this way and that way, and that's actually a complete lie. It's a legend. We've been building rooms canted and rectangular for years and years and years and years. We've actually done 500 rooms since the company started. So we've had our time to try different solutions. A correctly proportioned rectangular room is actually a very good listening environment. And by canting a wall one way, you may or may not improve things. Sometimes you can make them worse. If Murphy is not busy that day, sometimes you can make them better, but I wouldn't go there usually.
Well, now, most recordings, before you go on, most recording studios that I've been in, the control room anyway, is definitely not rectangular.
Right.
Are they operating on this myth?
They are operating on that myth. And when I've talked to the designers of those and I've said, have you modeled this? Did you know what the standing wave characters were here and there? Did you actually do the right finite element analysis or fluid dynamics analysis? I get a little bit of a blank stare and a little bit of the, it sounds great. What are you worrying about? And then when I go, well, let's see if it sounds great. And you play a bass tone and you move your head around and you realize, wow, they figured out a way to make it sound great at the seating position. And then just 2 feet to the right, it sounds bad. And that's not acceptable.
Where the producer is going to be sitting, probably.
Right. The producer is sitting in a place where they're hearing no bass and they're complaining, I want more bass. And then the mixing engineer has to go, come sit over here. And then that's how they resolve it. So rectangular rooms are fine. Now, what happens if you have a room that's not rectangular and it's open here and open there? Well, the same rules apply. You want to have about 15 to 20% absorption of the wall surfaces. You want to have some scattering surfaces, 15 to 20%, if possible, as much as 25%. And you want to have some kind of bass absorption. Realizing, of course, that if you have a listening space that's like this, and it's open to a long hallway that goes over there and reverberates for 2 days, you will hear that reverberation over here. It's going to come back later, and you may want to do something either in that hallway or put a drape. It doesn't have to be a hard surface. It can actually be a drape to reduce the sound, the amount of sound that's traveling back and forth from the hallway.
Mm-hmm. I was going to ask you about electronic room correction. You know, I'm sure that a lot of AV receivers most these days and preamp processors have electronic room correction in them in the form of Odyssey or Trinoff or Dirac, or Pioneer has a proprietary one. Yamaha has a proprietary one. What do you think of those? How effective are they compared with acoustic treatment to correct whatever ails the sound system in a given room?
That's a great question, Scott. So for the record, you need to get to good sound. And what I mean by good sound is the dialogue is clear, the localization is even, the integration from the front to the side to the back is all even, the bass is tight and punchy, everything just feels really natural. And actually, if you were so lucky as to be able to go to a good mixing stage where a film soundtrack or a music was mixed, you could actually go, wow, it sounds the same. To get to good sound, you need to have the right kinds of acoustical treatments working, and you need to have equalization. You need to correct the frequency response errors that the room is going to impose on the loudspeakers. Equalization cannot get rid of sound reflections. The sound's bouncing back and forth. An equalizer is not going to magically go, whoop, stop. You can't do that. What the equalization is going to do is it's going to neutralize, in a sense, the effect that the cavity of a room has on your loudspeakers. And I hope you can hear how the sound changes as I do this. A room's going to do this to your speaker.
Right. Just to describe to those who aren't watching video but only listening, you're moving your hands into your mouth, towards your mouth to make it resonant, and then you're moving them away, and you can hear a pretty big difference between those two situations.
Absolutely. So all rooms are going to resonate around a loudspeaker and change its tonal balance in some way. More at this frequency, more at that frequency, depending on the room. And that's what an equalizer is going to compensate for, is really the ill-fitting of the room resonances to the speaker. Mm-hmm. The acoustical treatments are going to correct really the time domain, if you want to think of it that way. So the sounds that are bouncing around the room, that are causing confusion in your brain, those get damped out and scattered by the acoustical treatments. And if you want good sound, you need both things. You need equalization and you need treatments. Start with the treatments and add equalization, and you'll end up with a great sound quality. Now, how do you do the equalization? There's no doubt in my mind that the best way to do it is to hire a competent sound engineer to come and measure and listen to your room and make decisions about how to adjust the equalizer to reduce some intensity over here, add some more intensity over at some other frequency, and do it by listening and by measuring. That's the right way to do it. Because today, no single test microphone really listens like the human being's ears and brains.
Right.
So that costs some money. You have to hire the technician for 5, 6, 7 hours to do that work, and you have to have an equalizer that's manual adjustable so you can do that work. And if you really are intent on getting good sound, you got to plan on spending that money, or else you're just going to be unhappy. Barring that, barring that, you can use one of the automated or semi-automated solutions out there that you mentioned. They just, for the record, they do a pretty good job. They just don't have a listening reference. They can't actually verify by their own ears, hey, did this work?
Right.
You know,
which is why that's just why I often recommend that if you're going to use one of those systems, use it, let it run, do its thing, but then go back and check the results and listen to some well-known content. And that's, I think, one key is listen to something you know well, and say to yourself, does this sound right? Or are certain frequencies too high, too low, as you say? And then go in and maybe tweak the results that the automated system gave you to improve things greatly. I also wanted to just point out that you said if you do 20% absorption, 20% surface area absorption, 25% surface area diffusion, and some bass traps, you're going to get 80 or 90% of the way to the ideal sound in that room. And the Band-Aid situation that you talked about, maybe a little less, but still significantly better. I guess my question is, when would you want to spend the extra money and hire an acoustician to come in and do what you were just talking about, spend some hours and have some expensive equipment and do all that thing, as opposed to just doing the basics yourself?
I think the answer is when you want a good result. If
when you want the best possible result.
When you want the best possible. I see people spending $350,000 on a top-flight loudspeaker, amplifier, and surround processing system, and then hit the auto EQ button and say, "Okay, I'm done." And that's a real disappointment. That's like you're going out to fish the most perfect salmon, wild Atlantic salmon, when it's just in the perfect time, bringing it home, sticking it in the microwave oven, hitting 3 minutes, and going, "I'm done."
Yeah,
you just don't do that. You cook it very carefully.
Indeed, I liken this to doing the basic picture controls in a TV versus doing a full-blown calibration, which costs several $100s and requires a professional. It depends in part on how much you've spent on the TV or the display. If you didn't spend very much on it, you're not going to spend a few $100. You know, just do the part yourself that you can do, and you'll get 80 or 90% of the way there. But if you spend a ton of money, it's worth investing a little bit more to get the absolute most you can possibly get out of the system.
Right. So it's not like if you went for an entry-level surround receiver and kind of midline loudspeakers, a proper tuning will definitely improve them a whole bunch. This is where it's hard to put a price on it. But you're going to spend a fair amount of money on the tuning, and maybe if you have a limited budget, maybe that's the right thing to do. Spend less money on the gear and spend the right money on the proper design of the room and the tuning of the room, because you'll end up ahead in the end. If, on the other hand, you're spending money on a top-flight receiver or separates, you owe it to yourself, you owe it to your investment to bring in a proper audio engineer and acoustician to check out how you set things up and then tune the equalization and level and delay professionally. I did want to mention this because you mentioned, well, listen to some known program material, and that can be very subjective. I do want to say that there are some great test discs available out there for audio, just as they are for video, so you can actually look at things that you're supposed to be paying attention to. There's a number of them on the market, calibration discs.
Any in particular that you can? Oh, you've got one. Okay.
I guess I'll put in a shameless plug for what's called the 5.1 audio toolkit, the TK51 as we call it. It's actually a Surround DX disc that's got about 90 different test signals and a complete instruction manual on how to use them. That you put the disc in your player and you listen through these different things, and you'll figure out, hey, is this working right or not? The first test signal I'd recommend playing after you've done the whole installation and calibration, either auto or manual, is there's a test signal that puts pink noise, wide band. It sounds like a rushing river, but wide band pink noise in the left speaker, then it hops to the center speaker, then goes to the right speaker, and then goes to the surround right, et cetera, all the way around a room. And they should all sound more or less the same. The tonal balance of that noise should sound even and consistent all the way around the room. If it sounds like there's giant differences, then you've got an issue going. Now, if there are differences, which one is right, which one is wrong? So the next step is to actually go out and buy a pair of these goofy little headsets like I'm using. So a company called Etymotic, Etymotic, makes these little earpieces. I'm going to unplug one. It looks like a little ear plug. It's got a great high-performance transducer in it that's compensated for what's called head-related transfer function. It sticks down your ear canal, sound that is compensated for the fact that it doesn't have your outer ear in it.
Right.
You listen to pink noise with these guys coming. Maybe you plug these guys into the headphone output of your receiver, or you found a source of pink noise on the internet that you put on your phone or whatever. You can get them anywhere. You listen to pink noise over these, and then you unplug them out of your ear, and you listen to the center speaker, and you go, wow, does this sound even close?
Good
and that's
idea.
a really cheap way to verify the work, because you can get these for, I don't know, under $200 for the better ones. They're cheaper for the lower ones. Make sure you go for this brand. This is, I don't work for them. I just like what they do. There's other companies making in-ear earbuds. They're not necessarily made for smoothness of sound. They may push the bass, push the treble, whatever. But this is the real ticket. And this is sort of the equivalent of what used to be called in the world of video an optical comparator, a grayscale comparator, where you're looking at gray comparing to what's on your monitor and going, I'm calibrated.
Right, right. Very good point. Very good point. Just a couple questions, quickies before we end here. One is, I got a question in the chat room. Oh, Web 1310. And I've wondered this myself. I've often heard people talk about what are the ideal dimensions of a rectangular room. And some people say, oh, well, they need to be related by the golden ratio, right? Which is this irrational number. Certainly, I've heard that you shouldn't have a cubicle room or a room in which the length is exactly twice the width and the height and so on. Are there any ideal dimensions that would help in the acoustical performance of a room?
That's a great question. And no, yes and no. There's a great paper also by, I believe, Floyd Toole on this about the ratios, and actually explores the golden ratio rooms and looks at their standing wave errors, and there are some errors. Here's the good news and the bad news. All of the calculations you can do by downloading a little spreadsheet or a little calculator from the internet that predict the standing waves at the length and width and height dimensions, in which you're trying to make sure they're all at different frequencies. If you build a cubic room, by the way, the resonance along the length, the width, and the height will all be the same, so that you'll end up with a triple whammy. That's a bad idea.
Bad idea.
Bad idea. If you can build a room that's rectangular, where the resonances along the length dimension are all at different frequencies than the width direction, and all at different frequencies than the height direction, all spaced more than 5 or 6% apart from each other, you end up with sound that is less bad, because they don't reinforce each other. All the frequencies end up being like an even spread like that. Now, the problem for most of us living in North America is that most houses are built out of walls that are sheetrock on wood or metal studs. And so at low frequency, those surfaces tend to buckle a little bit, and the resonances will actually be changed by the stiffness or lack of stiffness of the wall. So you actually can't really construct a room with normal construction and completely predict ahead of time where it's going to have standing waves unless it's a really solid boundary, as in stone or concrete. And why would you want to build a wall made out of concrete? Because it's going to resonate more. So the good news, bad news is that a room made out of a single layer sheetrock with studs is going to bow and buckle, therefore transmitting all the bass to the neighboring rooms. So the master bedroom next door is going to end up with a lot of bass. But it's also going to damp the bass resonance in the room and change the resonances to an unpredictable frequency. So it's hard to predict. It is predictable. You can actually, by doing fluid dynamics analysis at great cost, you can predict it. So I would say generally the advice would be make sure the room's not cubical, make sure it's rectangular, make sure that the dimensions are not even multipliers one of the other. And then with the rest, play with subwoofer locations, play with a seat location, have a bass trap in the room or 2 bass traps in the room to try to damp out the remaining resonances and equalize what's left, because by actually notching out a little bit the resonance frequency, you can reduce the audibility and the time character of the resonance.
Well, we've run out of time, and I didn't even get a chance to ask you about seat placement, which you just mentioned, or speaker placement. And we also had some questions in the chat room about isolating that room from the rest of the house or from your neighbors. Right. Will you come back and talk about that stuff another time?
I would love to. That'd be fun.
Fantastic. Thank you so much for being here. Anthony Grimani, president of MSR Acoustics. You can find out all about the products that he makes and the services of his company at msracoustics.com. Thanks so much, Anthony. Really appreciate you being here.
Thank you, Scott. See you soon.
You bet. You can find me, of course, at avsforum.com. You can follow me on Twitter at htgeekscott and at avsforum. And you can email me at scott@twit.tv. You can also find previous episodes of Home Theater Geeks at our own website, twit.tv/htg, and on YouTube at youtube.com/twit-home-theater-geeks. Next week, my guest geek is scheduled to be Mike Heiss, an industry consultant who's been studying HDMI 2.0 in great detail, and he has a lot of things to share with us about what that is now and what it will be in the future. So I do hope you will join me for that. Until then, geek out.